Okay, good. In case you need this for reference, or in case I do it without screwing it up, so come on, I'm going to get this. There we go. Okay, I've got the video pinned so I can monitor what I'm doing here to make sure you can see what I'm writing. Okay, so we have the impulse momentum theorem. And the impulse momentum theorem comes from Newton's third law and Newton's second law. Okay, if two objects interact, and I should probably say point-like objects, so you don't get any rotation out of this thing. If two point-like objects interact, then the forces they exert on each other are equal and opposite by Newton's third law. So the forces are equal and opposite. And the time of interaction is equal. And from this, we see that F12 delta T1 equals F21 delta T2. Well, in general, the impulse of a force is F delta T. And I'm not going to write it out, but that's where F is your force and delta T is the time. Okay? And we could say force acting for time delta T, okay, is F delta T. Now, if capital F12 and capital F21 are net forces, on masses M1 and M2. And I'm writing these, the notations are just a little careless right now because we've done this, but so this is kind of review. So a few things are kind of being taken for granted here, but I think the intent is pretty clear. So if these are the net forces on masses M1 and M2, then it follows that F12 delta T1 equals M1 delta V1. In other words, the change in the momentum of the first object over that time interval. And we can designate that as delta P1. And then the F21 delta T2 equals M2 delta V2 equals delta P2. Now, I said these were equal and opposite forces, but I made them equal. wasn't thinking as clearly as I would like to be. F12 should be negative of F21. Newton's third law says you have equal and opposite forces under these circumstances. Okay? If these are net forces, then this follows because F12 is equal to m1a, mass 1 times acceleration. So that it follows almost immediately that you get the m1 delta v. I'm not going to do the details of that. It's very easy to write out, very easy to understand. If F12 is m1 times acceleration 1, well, acceleration 1 times delta t1 is a change in velocity. So you got mass times change in velocity. So it's that simple. So very simple reason for this, and you want to be sure you understand it. Your book explains it, and I've explained it in the past. And if you want me to go on and do more explanation a little bit later, just ask and we can write it out. It's very straightforward though. Okay, so we have this. So since F12 equals negative F21 and delta T1 equals delta T2, it follows very easily that delta P1 equals negative of delta P2, because if delta T1 equals delta T2 and F12 equals negative F21, then this is the negative of this. Same time interval, equal and opposite forces. These two products will be equal and opposite, so the two momentum changes will be equal and opposite. Okay, well, one consequence of this, that again I'm not going to write out in detail, is the formula everybody memorizes so that they forget about impulse momentum, which is the fundamental principle. Okay, the formula is m1v1 plus m2v2 equals m1u1 plus m2u2. Now, not every author uses u1 and u2 with v1, v2. It might be v1 prime and v2 prime. Various ways to annotate this, and this probably isn't the way these are probably not the letters I used or the symbols I used previously. Probably did an M1V1 and M2V2, but probably didn't use U1 and U2 last time I did this. It varies. It shouldn't matter. Okay? What this means is that V1 and V2 are the velocities before interaction. U1, U2, the velocities after the interaction. And the interaction occurs for some time delta t. I'll also mention that this could also be expressed in terms of integrals. The integral of f12 dt equals the negative of the integral of f21 dt. And this is what happens if you have a variable force. Okay, here we're assuming kind of implicitly constant forces. If you have a variable force, you just take it over to an integral. And it would be from 0 to delta t, here 0 to delta t here, and I haven't written that out so you can read it, but you can read how your textbook annotates it. There's the idea. Okay, so we have all this, and this is really all there is to it. You just have to be able to apply it. So let's say now that we have the situation you asked about, let's say you've got a mass m1 moving at velocity v1 and a mass m2 moving at velocity v2. They collide. Now let's just assume a head-on collision for the moment. There's no reason to confine ourselves to head-on collision. These things could collide at any angle, and as you know, if you ever played pool or hit a ball with a stick, the angle at which these things rebound can be any angle practically, within your restrictions, okay? Like they can't pass right through each other. Although you can, well, let's not digress to that. Let's just stick with this, okay? So you've got M1, V1, and M2, V2, and I'm going to write a V2 like in this direction. So this thing now has to catch up to this thing, just the way I've drawn it. This is just a general drawing. You don't have to draw them approaching each other as long as they have velocities that eventually brings them together. Okay, so, and then after collision, you have, okay, over here maybe they've caught up, and just after collision, you have U1 and U2. And they don't necessarily, again, have to be in opposite directions. This thing could bump this one and lose some of its momentum. This will gain the same momentum. They'll go on. Okay, so now if the collision let's try to make it collision duration delta t, meaning they're interacting. There's a force acting. There's Newton's third law of force acting for some duration, delta t. What's the average force on each? Okay, well, we don't need this equation, although we might use this equation to analyze the collision if I give you the masses and the velocities. Right now, the question you asked was, about the forces and so forth. So let's go right to that. The average force on each is the change in momentum F12 equals, we'll say delta P1 over delta T. Okay, what's the change in momentum of this first object? Well, the change in momentum, we're changing from V1 to U1. So the change in momentum is going to be U1 minus V1 over delta t. So if you know U1 and V1 and the duration of the collision, you can easily find the force. I'll do a numerical example in a minute. And then similarly, F21 is going to be delta P2 over delta T, which equals U2 minus V2 over delta T, and this is going to equal negative F12, so that this and this should be equal and opposite. And if they aren't equal and opposite, that means you screwed up your analysis. Or it means whatever the collision is, if somebody said here are the velocities before and after collision, it means they screwed it up. Okay? If you have valid initial and final velocities, you have this. One more thing I'll mention is the system has to be isolated because these are said to be the net forces. the force of interaction is the only force acting. That means there's no frictional force. Nobody's put a voodoo on the thing. Those are the only forces that act. And that's what we mean by an isolated system. So again, let's just mention that. Isolated system comes down to F12 and F21. Being the net forces. If I had room, I'd say the net forces on the two respective objects, but I think that's understood. Okay, so again, you see isolated system. I think I remember when I took physics, I was never quite sure what an isolated system was. I just said, okay, it's isolated. Now the equations work. Okay, well, it comes down to just net force. Okay, which is can be a fuzzy concept, especially in the beginning of a course. Okay, well, there we have it. Now let's go ahead and turn to a numerical example.